Hey everybody. Um, Get to the end of the unit now. So what we do is we hit the next part of this unit in acid bases called acid-base reactions and neutralization, which includes the method of titration. So it sounds like a mouthful, sounds like a lot, but it's actually kind of simple. We're going to hit it fairly briefly. We'll cover just a quick titration lesson, and then we'll do a little practice, and then you'll be on your way. All right, so first things first is some acid-base reactions, and generally speaking, what we do is if we look at this really quickly, just a little review on the single replacement stuff. If we look at single replacements, we're going to recall that acids are going to react with groups 1 and 2 metals to form an aqueous salt and H2 gas. Now, again, group 1 and 2 metals is mostly what you'll see here, but you could also react with zinc. You can react with some of the transition metals in the first row. I mean, what you want to try to do is look for table J on this. So table J in the New York reference tables would be a good spot to look, and you'll see that they'll give you an order of reactivity. So we'll review that again a little bit later. So a good example of this is taking magnesium. We reacted with HCl. If you remember, magnesium is higher on the table than H, which is your acid, so it will react spontaneously in that direction, and we will create an aqueous salt, and then here you have your hydrogen gas. So that's typically what happens in these single replacement reactions. Okay, and there's a picture of you can see the bubbles forming when this piece of magnesium is placed in the hydrochloric acid. And next thing's called neutralization. Now, neutralization, you probably heard this before, where an acid and a base react with salt and water to form salt and water. Now, interesting is that when you mix these, the H plus ions from the acid will react with the OH ions from the base, okay, and then you will form your water molecules. And this was found very early on in science when scientists first discovered acids and bases, and when they mixed them, they realized that their properties would actually cancel out. All right, the remaining ions left over, okay, are going to be an aqueous salt, and this process, again, given the title here, is called neutralization. Okay, so really, what you really want to realize is what the acid is, what the base is, and realize that this is going to happen in a 1 mole to mole is a 1 mole to mole ratio, which means one H and one OH will get together and it will form a water molecule. You can see what our water molecule looks like, and you can see one of the H's and one of the OH's, if they were to bond together, they would produce an acid. So you can see water molecules actually have a base side and really an acid side to them, if you can think of it that way. All right. What's left over is typically your salt and what's left over is your ions is your salt. Okay. So for example, if you take a look at hydrochloric acid and sodium hydroxide, again, you can see the H and the OH. The H, when you mix them, will go with the OH, Na with Cl. But again, this is pretty much going to stay soluble. So what you would end up having is in Na and Cl aqueous solution. Again, this is going to take place in water, and you'll create new water molecules. So again, you're really doing a double replacement. You're doing the double switch where the 8 plus and minus and the plus and minus will just do their switch typically. Okay. If you want to take it a little step further, you can take an acid again and a base. But in this case, things are a little interesting because this guy actually has two OHs. So you have an OH minus and an OH minus. You have two of them. So you're really going to require not one H, but really two H's to balance that become neutral. So that's going to help you balance the equation. So if you take Ba and Br, you get BaBr2. Okay, and you'll get your water as usual. However, you're probably going to need it too because there's two OHs here and two H's, okay, are going to make two water molecules. So balancing a reaction like this is actually fairly simple um, because what you can do is you can use your water as a way to balance. All right, so that's what you can do on this. Another way you can see this is in this case, you're going to have two H's for sulfuric and one OH for this. So if you switch it, you'll get potassium sulfate. Okay, and you'll also get your water molecule. In the case this way, again, you have two H's. You're going to definitely need two OH's, and again, you need two water molecules. Okay, and lastly, but not least, if we take aluminum hydroxide that has three OH's, you guessed it, you're probably going to need three H's. Okay, you'll get your salt, aluminum nitrate, and again, you'll get your water, but this time you'll have three waters. Okay, don't forget your crisscross method. So if you're going to take Al and NO3, just to review, you take your Al is 3 plus, right? And NO3 is going to be minus charge. And remember that when you bring a 3 down for the polyatomic ion, we have to make sure we use parentheses. Okay, and that becomes that beautiful thing there. Okay, so just to review a little bit with your formula. So what's the big deal here? An acid plus a base is a salt and water. Okay, and if this takes place in a 1-to-1 ratio, mole ratio, then you would exactly cancel out the acid and base. Okay, so that's interesting to know. Make sure you can recognize this as a neutralization because of the salt in the water. All right. Uh, and interesting enough, and if you know where you may ask, well, where does this happen in real life? Well, in the stomach, we actually have hydrochloric acid. So in the stomach, we have where is my colors? Quickly, sorry. In the stomach, we have hydrochloric acid, and what you can do is you can take something called an antacid. Many times has magnesium hydroxide in it, right? So you can use that as a way to neutralize the acid in the stomach. So the OH would combine with the H in your stomach. That would cancel out and produce water, and then you'd be left with magnesium chloride, which is a lot easier on the stomach than the acid. All right, so that's a good way to see it as we go. All right, next step, and this is called an acid-base titration. Okay, and don't really worry about the word so much here. The word is really a way that we can use a method for finding an unknown reaction, an unknown concentration of something. So basically, if we know the concentration of something uh, and we react it with a known concentration, all right, so if we know the concentration of something, we react that with an unknown, and we know where that is going to be as far as neutral goes, then it's going to allow us to calculate the unknown. So really what's doing is using a known to find an unknown. All right, so that's really the key. So an unknown concentration of acid base can be found by reacting with a known solution or standard solution. So the known concentration, okay, that's going to be called standard. Okay, so that will be our standard solution. Our standard solution, okay, is going to be the one you know the molarity of. Okay, let me get back to my colors here. Okay, all right, so the known is called your standard. Okay, and of course the unknown, you don't know what that is, so that's usually our X, right? So what we'll do, and we're going to do this, okay, until the moles of acid, we're going to react them together, and we're going to wait, and we're going to keep reacting until the moles of our acid is equal to the moles of our base. And when we know that's the case, we reach something called the equivalence point. So equivalence means they're equal. So there's a little clever way we could do this. All right. And what we're going to do is we're going to use an indicator because we can't really see this. We can't see the molecules. What we're going to do is how we're going to know that we've reached this equivalence point. Well, what we can do is use something called an indicator. Or you can even use a pH meter to tell us when we've reached that neutral point. Now, if we don't know the acid, let's just say we don't know the acid, but we know the base. Well, if I don't know the acid, but I know the base, and I can react them for when they're equal, then I can use a calculation to figure that out. Now, with the indicator, when the indicator tells you that you've reached this acid equals base spot, there's going to be a color change. And when that color change takes place, that color change is going to be called the end point of the reaction. All right, so that's what we're going to see when we do this. Okay, so how do you actually do this? Well, if you take a look at this setup, okay, what we're going to do here is we're going to use a titration setup. Now, some of them look like this. This is a very, crude way to see it, but you're going to have something called a burette. A burette is a long tube, okay, and a burette starts at 0 at the top, and let's just say it ends with 50 milliliters down here. So it's sort of like an upside down graduated cylinder. But what you're going to do is you're going to have a little screw here, and what that does is when you turn that, it's almost like a water faucet. What that's going to do is when you turn that, it's going to allow uh, solution to drop off out the bottom. So if you start at 0 here, okay, if you start the meniscus here, and you let this drop, you can let it drop, 10 milliliters, 20. So if you want to let 20 milliliters out of here, you can start from here, wait till it drops to 20, and then you've dropped 20 milliliters out. So that's going to be the important part. All right. So what we're going to do is, let's just say we have some unknown acid, and we want to find the molarity of some unknown acid. We want to find the concentration of some unknown acid. So what we're going to do is we're going to put some acid in this beaker. Okay, so we're going to put some acid in this container. Okay, and I'm going to use 10 milliliters. Okay, of this acid. All right, so I'm going to choose 10 milliliters. I can choose however much I want, but I'm going to just choose 10 milliliters just for the heck of it. Okay, and what I'm going to do, so this is going to be, acid is going to go in the bottom here. Okay, and in the burette here is, we're going to put in the burette in here, we're going to put 0.2 molar NaOH. Okay, so I do know the concentration of that, so I know that for sure. So that's going to go in the tube with this burette. Okay, and there's going to be 10 milliliter of acid that I don't know the concentration. So I have X molarity here. So I don't know what molarity is. That's what I'm looking for. Okay, and my idea is, if I start, and I'm going to also put an indicator in here. Okay, so my indicator is going to go in there, a couple of drops of indicator. Okay, and I'm going to put 10 milliliters in here. I don't know the concentration. And what I'm going to do is, I'm going to react. I'm going to turn the screw, and I'm going to react the base. Okay, because again, base is going to be in here. Acid is going to be in here. And I'm going to react the acid base. I'm going to drop the base into here. I'm going to mix this, okay, until they reach the neutral point. And when they reach the neutral point, this indicator is going to let me know when they're equal. And when they're equal, if I know the base, then I can calculate the acid, and I can figure that out. So that's called a titration. The lab setup here is called a titration. Okay, so what are we going to do? We're going to fill out this table. Okay, now what we can normally do is fill out the burette readings on how much we're dropping in here, because when we put acid here, base, we're not going to know how much we're going to add. We have to wait until we get to the indicator. So that's what we're going to figure out. So what I'm going to do in here, um, okay, what I'm going to do is, the initial is going to be the high burette point. So right now, I'm not using a burette point for the acid, because the acid, I just put 10 milliliters in here. So I don't need to know any of this. This is out. Okay. However, what we want to do is start off with and write down where we're starting with my burette. So I'm starting in this case with 0 milliliters. Okay. And what I'm going to do, is I'm start this going, and now I'm going to start dropping this acid in little by little. Okay. So I'm going to use an indicator to tell me when it's complete. Okay. My indicator goes in with the acid. Okay. So first things first is record my starting volumes of my acid base. So I just did that. I recorded my 10 milliliters here of my acid. All right. And I'm going to record my starting milliliters of my base, which is going to be 0. All right, and now I'm going to start reacting. So I'm going to slowly add the standard solution. So I'm going to start dropping this in, and dropping this in, and dropping this in, and dropping this in, until it hits the water, okay, or this acid. And I'm going to start, and I'm going to keep stirring it. So I slowly add my standard solution by stirring. Okay, I'm going to slow down my titration when the indicator begins to change color. So you can start to see a color change within here. All right. Now, if I decided to use phenolphthalein, phenolphthalein, what I'm going to get is like wrong color. Now, phenolphthalein is colorless in an acid, but when I hit the base, I have trouble with this. When I hit the base, eventually this is going to turn magenta. And when that turns pink, I know I've hit my level. I know I'm good. All right, so I'm going to record my starting values, slowly add the standard solution. Eventually, I'm going to slow down my titration until it begins to change color in the correct range. And then, boom, once it changes this magenta color, I know I can stop reading. Now, let's just say I stopped reading, okay? And I stopped reading, and I stopped reading when this reached, I don't know, I'm going to make this up here. And let's just see this drops now to this level. It goes down here. All right. And it drops until it hits 11.7 milliliters. I'm just going to make this up, this number. Okay. So that means how much did I drop? I always take my final minus my initial. Okay. And that's how much. So it's the final volume here minus my initial. So the final minus initial is going to be 11.7. Okay. Now be careful because you don't always have to start at 0. You can start at any of the BRAT readings. All right. So final. Now, once that's done, I'm finished. I have what I need. Right. I have my amount of volume of base that has canceled out or neutralized the amount of acid that I have. I also have the molarity of my base. So I can find the molarity of acid by doing something really simple. Okay, I can find my amount used, which is I just did. I subtracted the final initial readings. Okay, and now what I can do, and again, this was my 11.7. Back a notch here. Okay, I could take. I had my 0. I had my 11.7. Fill this back in. All right. I have this number, and this number. I'm going to need my standard. Okay, so I'm going to calculate the molarity of the unknown acid or base. Again, you could use acid base. Okay, and since I know the molarity is moles over liters, I do know that the molarity times the liters is the number of moles. So if I could take the moles of H and the moles of OH, again, this is true for both, and I know that's equal, I could simply take the molarity times the volume of the acid times the molarity times the volume of the base, and I simply can do that, and I have 3 numbers. So basically, I have my molarity. Sorry, I have my volume of my acid here, right? Because this is the acid. I have my volume of the base here, which I determined from the titration, and up here I have my molarity of the base, and I can make that molarity of the acid could be my X. So very easy to do here. All right. So that's what I'm going to do. I'm going to take my again my 0, my 11.7. 11.7. Okay, very easy. So what I'm going to do is I'm going to take MAVA equals MAMBVB. Okay, I have my molarity of my base was given to me to be 0.2 molar. My volume of my base is going to be given to me by 11.7. Okay, and then I have my volume of my acid, which I used in the beginning, and I'm going to do that by X. So if I hit my calculator, if I take my 0.2 times 11.7, I divide that by 10, and I have 0.234. So basically, the molarity of my acid is equal to 0.23. It's probably moles per liter. And that's it. Okay? So what I normally would do is, again, I would probably do this again, and you can see it may kind of make sense. If you have a 0.23 molar solution and you're about the same concentration, you'd expect it to neutralize using about the same amount of volume. And that's really what we use here. So that's really a simple calculation. So keep it real simple. Again, this is a strong acid, strong base titration. If you used weak acids or weak bases, the calculation would be much more complicated than this. So we're going to stick to just a strong acid, strong base calculation. But this is very simple. Using this allows us to really experimentally determine any amount of acid or base. All right. So moving on a little bit, a little quick practice here, and we can take it from there if we want to practice just real quickly. So it says how many milliliters, how many milliliters. So we're looking for the volume of 1 mole KOH is needed to exactly neutralize 90 milliliters of a 2 molar solution of hydrochloric acid. Since we're exactly neutralizing, we could say MAVA equals MBVB. Okay, very simply. So we know this is the base here. We know this is the acid here. Okay, a good little trick here is usually the numbers are paired pretty well. So you could just put them in the equation. That's pretty easy. Okay, so 90 here, milliliters times my 2.0 molar. Okay, and they want to know how many milliliters that you need. but we have a 1 molar KOH solution, and you want to know what X is. Okay, and this is kind of easy because if you think about it, if you have a 2 molar solution and that's twice as sweet as this, it's twice as concentrated. Okay, and you have 90 milliliters of this acid that's twice as concentrated, you're going to need double the amount of volume of the base, right? Because it's half the molarity. So of course this would be 180, and again mathematically you could do that too. All right. Similar scenario here. I'm not gonna. I won't write this out, but I could give you the answer really quickly. You would take 250 times 4.0. Okay, and you divide that by 500. Okay, you would get about 2. So the answer would be, the answer here would be 2 molar solution. Okay, so pretty simple stuff there. Okay, again, these are the very same kind of thing here. If you look at the bottom, in fact, identical questions, you can just look at it here. Again, this problem here is a little bit more complicated. Here, you're looking at unknown base. So your unknown base, and again, your acid here is molarity. So you do have the molarity of the acid here. Okay, and you're looking at this table of titration data. So basically, you're looking for an unknown base. So your MB is what your X is. You don't know what that is. Okay. So then again, from the table, you're going to have to get the other information. So in this case, they give you the burette readings, but they don't give you the difference. So you can't use the final volume of the burette. What you want to do is the difference. So you have to make sure you take the final minus the initial here to get those answers. So it's really important that you do it the right way. So you want to take the final volume of 22.9, and you want to subtract that from 7.5, and that's how much you used. So again, you need to get that information of how much you use, which is about 15.4, okay, milliliters. And for the base, you want to take your 33.1 minus your 11, which would be 22.1 here. All right. So again, this is the amount that you used. This is the amount that you used, and that's what you need for the calculation. So now we have what we need. So we can say MA VA equals MB VB. Okay, we know what MA is. That's easy, right? MA is going to be 1.4 molar. Okay, our volume of the acid is going to be our 15.4. Okay, milliliters. That we got how much we use from the burette. Again, you don't want to use the final volume because you don't know what you're starting with. You want to use the difference. Okay, we want to find the unknown base. We don't know that. Okay, and then we'll multiply that by the base, which is your 22.10. Okay, so that's easy algebra right there. Again, setting up is a big deal. Okay, and then we can take 1.4 times my 15.4 is that thing divided by 22.1. Okay, and I get about 0.98, 0.9, and about 0.98 molar. Okay, and that's going to be KOH because that's the base. Okay, so again, it's not hard. Again, this is number 3 here is probably the hardest one you'll get, and the more difficult one as far as the regions goes, only because you have to find the final volumes here before you do anything. Not using the final volume of the burette. You need the final volume used. Okay, that's the important thing. Okay. All right. So really quickly, you can play around and just review a little bit. Which beakers would have a neutral pH? Okay, if you mix them. Well, I'm saying just in general neutral pH. This would be neutral. Oops. Notch there. Sorry. The wrong color. I guess we could use this bright pink, right? Neutral would be this guy and this guy, because that is a salt, right? And this is an alcohol. Alcohols are not acids or bases, okay? And this is a salt, which is not necessarily acid or base. So you could say D and E is your answer here. Okay, which beakers could have a pH of 12? Okay, again, you're thinking base. Okay, be careful. Alcohols are not bases, so it can't be that one. Here's your base here. All right, so your base would be C. Find the formula for the salt produced when equal volumes of beaker B and C are mixed. Okay, B and C. B would be CH3COOH, which is Cu, right? Again, that's the H plus. And you would mix that with beaker C, which would be your, sorry, this would be your acid. Your base would be KOH. Okay, this H and this OH would make water, and you'd have potassium. Basically, you'd have potassium CH3 Cu like this. That would be that. Okay. Which beakers are electrolytes? Again, acids, bases, and salts. Those are your electrolytes. Remember, we drink electrolytes, we exercise, we get good abs. Acids, bases, and salts. So here's your acid. Here's your acid. Here's your base. Here is your salt, right? So you want to go A, B, C, D, E, not an elite. Important, not an electrolyte. Okay. Carbon and an OH is an alcohol, not a base. Describe the color change of phenolphthalein if beaker C was added to beaker A. Beaker C, okay, is a base. So you would start off with pink, correct? In phenolphthalein, and if you added acid to that, you would go pink to colorless. Right? All right. When you're dissolving equation if you want the dissolving equation for the solution in beaker D, okay, in beaker D, you would say NaNO3, which would go to Na plus NO3 minus. That was just simply a simple dissolving equation, a little Regents review there. Sounds good to me. Moving on. Okay. Now, what if you had a situation where you had multiple hydroxides? Okay, for example, acids. Okay, most of the time you're going to have something called a monoprotic acid, which is an acid with one H, which is HCl. There's only a single H here. Okay, diprotic acids, di meaning two, is example of an acid with two hydrogens. You'll see the two hydrogens there in sulfuric acid. Triprotic acids would have three here. So you can see that's the case. Okay, bases can have multiple hydroxides also. You'll see calcium hydroxide has two, OH has two. Now, this presents a problem sometimes because when you're neutralizing and you want to figure out how much there is to neutralize and you know the formulas, you have to make sure that, again, 1 mole of H has to equal 1 mole of OH so that you're neutral. So if you start mixing multiples, you're going to have to take it into account for that. So here's the rule. Include the number of H's and the number of OH from the formulas, if you know them, into this equation when you need to. So for example, okay, I'm going to show you what we're talking about. How many milliliters of a 0.5 molar calcium hydroxide solution are needed to neutralize HCl? Okay, well again, let's go back to our MAVA equals MB formula. Okay, again. Now, what we're going to do is we're going to add something to this formula. Okay, so I want you to make sure you check. Now, if you see that there's two hydroxides and it doesn't match two H's, so these should always match in number. Because again, 1 mole must, remember, again, 1 H and 1 OH makes 1 water. If you have extra of each, then you're not going to neutralize. You want to make sure you neutralize. So if you see that they're different, what you're going to do is go to the base, take how many hydroxide you have, and times this side by 2, times the base side by 2, because it's 2 OHs. And then simply what you'll do is on the acid side, you'll times that by 1. Now again, do you always have to put the 1 as the 1 cancel? Yes, it does. Now you can go and answer the problem plugging the numbers in. But you have to make sure you make that adjustment if the acid and base are different. Okay, so now we can put in the molarity of the base here, 0.5. Okay, we want to know how many milliliters. That's the volume. We can make that X. Okay, the volume of the acid is going to be 50 milliliters, and we have 0.5. Okay, and then you can solve accordingly. So I'm not going to give you the answer here. You can go ahead and do that. That's kind of easy. Okay, so that's that. Okay, and then we can figure it out that way. So that's I'm just giving you the answer in that way. Okay, so in this one here, again, I'm not going to go through the whole all the answers. You can get them in class. Again, calcium hydroxide again is OH2. So you're going to have a 2 to 1. Okay, looking at this one, you're going to have a 3 and a 2, right, on each side. This is going to be the base side. This is going to be your acid side. So make sure that you put the 2 on the acid side and the 3 on that side. Okay, and again, you're going to have a 2 here, and you're going to have a 1 there. So make sure you make those adjustments to those parts. Okay, and again, you can look this up a little bit later. All right. So that ends the show on this. Again, I know this one is a little bit long. It's a lot to do. Uh, but again, ask questions in class. And again, if you have to go over it, and we'll see you soon.